Hello and welcome to our tutorial regarding our elliptical waveguide design tool. We will start with a quick introduction before we continue with an overview of the tool and finish with a use case. Let's start with the introduction. You will find the elliptical waveguide design tool on our website at hokua-rf.com. Go to the section Design Tools and click on the category Transmission Lines. Here, you scroll down and select the tool. Let's continue with the overview. The left column is dedicated to the mechanical parameters of the elliptical waveguide and the resulting cutoff frequencies of the first 10 waveguide modes, while the right column is dedicated to the performance of the elliptical waveguide in terms of wavelength, wave impedance, propagation delay, and attenuation. Let's focus first on the left column. At the top, you have to specify the mechanical and electrical parameters of the conductor. The numerical eccentricity is solely given as helpful information. Afterwards, you have to specify the dielectric parameters of the filling material, which is most often just air. The specific cutoff frequencies of the first 10 elliptical waveguide modes can be calculated with an accuracy better than 0.03% thereafter. Detailed information on waveguides and waveguide modes can be found in our table Waveguide Types in the section Converter and Tables. The link leads you directly there. Let's proceed with the right column. At the top, you have to specify the operating frequency. Afterwards, the resulting wavelength in the direction of propagation and the wave impedance are calculated for the waveguide mode of interest, as long as the operating frequency is above the respective cutoff frequency. The propagation delay and the attenuation are only available for the first elliptical mode TEC11. The references are an excerpt if you want to dig deeper into the mathematics behind elliptical waveguides. Let's finish with a use case. We would like to present the performance characteristics of a Ka-band elliptical waveguide, which could be used in radar applications to connect the RF front end with the antenna. The mechanical parameters are chosen such that we have single-mode operation of the elliptical waveguide at 28 GHz. The waveguide has a length of 1 meter with semi-major axis A equal to 5 mm and semi-major axis B equal to 2.1 mm. This results in a numerical eccentricity of 0.9 for the elliptical waveguide. The conductive material is copper, while the filling material is simply air. Let's have a look at the mode chart with the cutoff frequencies of the first 10 modes. The cutoff frequency of the dominant mode TEC11 is 17.9 GHz, while the cutoff frequency of the second mode TEC21 is 32.8 GHz. This permits operating the elliptical waveguide solely with the dominant mode TEC11 at 28 GHz, with multi-gigahertz bandwidth for radar applications. Let's have a look at the attenuation of the elliptical waveguide. At 28 GHz, the attenuation of the 1 meter waveguide is barely 0.4 dB. The attenuation minimum occurs close to 42 GHz, which is, however, not a good operating point. Here, any waveguide discontinuity could excite higher order modes, of which 4 modes, including the dominant mode, would already propagate through the elliptical waveguide. This would result in a significant increase in attenuation due to mode conversion, as well as severe dispersion. Let's have a look at the electric field of the dominant mode TEC11. A slice of the elliptical waveguide is shown in the upper left-hand corner with field arrows representing the electric field. The electric field strength is color encoded on the surface of the elliptical waveguide. The lower right-hand corner shows the dominant mode TEC11 propagating through the waveguide. The mode is excited with a specific rise time at 28 GHz. Finally, let's have a brief look at the mechanical construction of the elliptical waveguide. There is a multitude of options to manufacture waveguides. A split block design, as shown on the right-hand side, is especially useful when you want to integrate components in the waveguide and simply CNC machine both blocks. Moreover, extrusion molding or cold hammer forging, as shown in the center, or even metallizing low-loss dielectric materials, as shown on the left-hand side, are other possible alternatives to manufacture waveguides. Nowadays, additive manufacturing or 3D printing offers highly flexible design and manufacturing options. However, every manufacturing process is completed with some form of electroplating, sputtering, adhesive bonding, or injection overmolding in order to apply a low-loss metal coating to the waveguide. Depending on the required mechanical robustness, accuracy, and RF performance of the waveguide, a specific manufacturing process is chosen. We hope our tutorial was helpful to you. Thank you for watching and have a good day.